So that's great. We took some time, the first hour or so of class here, to learn what the units are, and from here forward, we're just going to be using those units. Okay, but let's talk about, now that we know what they are. Let's talk briefly about how we use them. Okay, so the coulomb per kilogram that we used, we said can be used to measure entrance skin exposure, but isn't necessarily any longer. That's great for talking about the primary beam. You can use coulomb per kilogram as a physics unit, and it's appropriate for describing the X-ray beam as it leaves the X-ray tube. If you took a radiation detection device, stuck it in the path of the primary beam, leaving the X-ray tube, you could measure the energy in the primary beam. You could, in principle, use that unit to know what the entrance skin exposure is, but we instead like the unit, the gray, for that. So the coulomb per kilogram is great for measuring the energy in the primary beam. All that coulomb per kilogram can tell you is how much ionization, how many ionization events are happening in the air where the radiation is, the air that's been exposed to a source of radiation. Okay. The gray, as we learned, is another physics unit. It deals with energy and movement, so it's a physics unit. And it can describe air kerma or tissue kerma. We didn't call it tissue kerma earlier. We just called it absorbed dose. But all it is, it's saying, here's a unit that tells you how much energy is deposited, absorbed, into any substance. As I said earlier, you are no different than the air in the room at the atomic level, right? You are solids, liquids, and gases. The air is a gas, okay? But you're all made of atoms. So we can just talk about how much energy is deposited into your atoms versus the atoms in the air. And we can talk about that all using the unit of the gray. And recall that sieverts talked about biologic harm. We can use the sievert for dose equivalent, which takes into account the type of radiation. And we can use as well the sievert to talk about effective dose, which would include the type of tissue. The gray is often used to talk about patient dose, but as an X-ray tech, are you being exposed to radiation on purpose or on accident? Like, do you mean to be exposing yourself to radiation if you do? Right, and non-purposeful, right? Your goal is to not expose yourself to radiation, right? That's why we have the control consoles. That's why we have the leaded glass windows. That's why in all cases, no matter what, we're going to try to stand 6 feet at least from the patient. We'll learn that number later. Why? Because our amount of radiation is not intentional. We'll often use the sievert to talk about the employee, the occupational worker, us, right? So our yearly dose limits, which we'll get to talk about in a little bit here, those are given in sieverts, not in grays, okay? Where the gray is often used to talk about the patient. Okay. One small side note, because the monitoring companies are slow to catch up, the badge, so all the testing you guys do is using these units we learned. All of the textbooks use these units we learned, but some of the badge monitoring companies, personnel monitoring companies, are continuing to report units in the old units, okay? Report dose in the old units. They'll use something called the REM. You guys remember the REM hopefully from last time, right? Radiation exposed man, okay? The REM is the unit used for the occupational worker, us. And the unit is given as a millirem, 1/1000th of a rem. And that's given on the quarterly badge reports or monthly badge reports. And so to convert those two, the best way to do it is to convert millirem to microsieverts. Okay, so it's multiplied by 10. 1 millirem equals 10 microsieverts. That's the thing to remember here. So I would write down for remembering 1 millirem equals 10 microsieverts. That way you can understand that. Yeah, so if you got 5 millirem, you were exposed to 50 microsieverts. You had 50 microsieverts of dose equivalent. Okay. And just to get one more on the table, because there are more. We're not going to use it so much, but we should be familiar with it because it will come up in sort of conversation. The gray, the sievert are great for measuring energy deposited in biologic harm, but if we want to measure radioactivity, right, something that can't be turned off, right? So you should know that your X-ray machine is only creating radiation as long as the exposure lasts for. The exposure lasts for 1 second, well then there you go, okay? The exposure lasts for 500 milliseconds, then that's how long the radiation is happening for, okay? However, with a radioactive source, like uranium, polonium, lead, in some cases isotopes of lead, potassium-40, those radioactive elements, they don't turn off. That's why they're dangerous, right? They just are radioactive. We measure their radioactivity, or we can measure their radioactivity. That's not measuring how much exposure or how much absorbed dose a patient would have. That's simply measuring, in this case, how many decay events happen over a period of time. The time period is typically 1 second. The unit here is called the becquerel, capital B, lowercase q. And a becquerel is 1 decay event per second. So if a source had a radioactivity of 100 becquerels, there would be 100 decay events per second. That's how that would be considered the rate of radioactivity. So this is the unit for, this is 1 unit for the rate of radioactivity. Becquerels given in decay events per second. This can be one of 3 options. What are the 3 options for radioactivity? What types of emissions can happen? We've been talking about them all day. They're given by Greek letters.
Alpha, beta, and gamma.
Alpha, beta, gamma. Good. Alpha and beta radiation are particles, right? Pieces of an atom. Gamma is different though, right? What is a gamma ray? What type of thing is it? So this would come from last lecture. What does it say here? Each decay event can be the emission of an electromagnetic wave or a particle from an unstable sample. Alpha and beta radiation are particles. So what then must be a gamma ray? Sarah, what must a gamma ray be if alpha radiation and beta radiation are particles? Can you see what's written up here? It says each decay event can be the emission of any electromagnetic wave or a particle. Alpha and beta radiation are particles. So what must a gamma ray be? A wave, an electromagnetic wave, right? Those are the only options. Radiation is either an electromagnetic wave or it's a particle. The only types of particulate radiation that you guys are learning about right now are alpha and beta. Helium nucleus is alpha, and an electron, fast electron, is a beta radiation. Everything else is an electromagnetic wave. Okay? Electromagnetic waves that come from radioactive elements are called gamma rays. Okay, so that's how we measure radioactivity. Okay? Good. So let's sum these up, and then we'll move on to learning about detection devices and dose equivalent limits. So our basic units, to sum it up here: the gray, the sievert, and the becquerel. The gray, the first one, air kerma or exposure, energy absorbed in the air. Okay, that can be given in joules per kilogram. The gray. I haven't told you what a joule is, but know that a joule is a unit of energy, okay, and it can be used to express any energy in electricity, electric energy, I guess you could say simply. But you'll get it. I will give it to you later on, but for right now, it's a unit of energy. The next gray, so that would be the first gray at the top for air kerma or exposure. That's gray in the air. Right, that's gray with a subscript of A for air. Gray with a subscript of T for tissue is tissue dose, energy deposited or absorbed into the tissue. The same unit though, joules per kilogram. Sievert is dose equivalent, indicating biologic harm. To know the sievert, you needed to know how much was absorbed. What's the other thing you needed to know the sievert? It's going to tell you the amount of harm, right? In order to know that, you needed to know how much, right? What's the other thing you needed to know about the radiation? The type, right? Such as alpha, beta, gamma, or X-rays. The becquerel gave you an amount of radioactivity, decay events per second. 1 becquerel is 1 decay event per second. And there's lastly, and this next slide has a few, but I'm only going to point out the one important one that we'll need. Lastly, where the laser pointer's at, effective dose. Effective dose, for X-rays, effective dose can be expressed in sieverts or grays. The effective dose indicates how much harm, but specific to a type of tissue, right? So you have to include what's called that tissue weighting factor. Okay. So here, this is the summary and sums up what we learned about what those units are.